All right, let's. We have a good grounding. I think we've taken the first couple of chapters very slowly. Let's start to move on a bit. Chapter 3, mostly, is to do with smog. What it specifically says is we want to know about pollution at the ground level. Okay. Yeah, you talked about the ozone layer. Yes, it's important. It was important enough to have multilateral agreement on how to remediate what was going on. But it's up in the sky. It's 25 kilometers up in the air. Um, People have completely stopped talking about it. One of the prompts in your homework essay is, so why have people stopped talking about the ozone hole? Yeah. Whereas if the pollution is bad in your town today, people will be talking about it today. And the first one we'll pick up with is smog. And it turns out that there are two types. There's the industrial or sulfurous smog. This is the type of weather condition that we used to see in London, don't anymore, because they legislated it away. London had a reputation for being a very foggy city. And sometimes the fog was so bad that you couldn't see to the end of the street, and they called it pea soup. Like, is pea soup even a thing over here? Yeah, okay. You can't see through a pea soup. It's not a broth, it's not translucent, you can't see through it. You only get the surface. Yeah, and the fog was pea soupers, and we had these through the 1800s into the middle of the 1900s, even post World War II. And then somebody just had to do something about it. And it's a combination, both the smogs we'll see are a combination of stuff that is man-made and natural. Okay. Smog, if you've never figured it out, is a diminution of smoke and fog. The man-made part of industrial smog is smoke. And that smoke is from wood fires and coal. And, oh, I'm using my phone for this. If we were to pull up how many tons of coal are consumed in Europe over the past maybe 100 years, you would see this. It's down to a really, really tiny amount. And the impetus to move away from coal as a means of energy generation and of heat generation is twofold. It's dangerous and it's polluting. It's polluting in a number of different ways. You have to mine it. I had family members in the mining industry, and nobody's happy about being a miner. It's an incredibly dirty, dangerous, and then chronically dangerous job. So both acutely dangerous because mines collapse, people get injured, and then chronically dangerous because of things like black lung, where you breathe the coal dust. Yeah, really, really bad. In fact, I would posit that this actually goes like that. Somewhere in the 80s.
Between 1990 and 2020, coal production fell by 80%.
Yep. So if we put 1990 in here, that is an 80% drop. In what, 20 years?
Yep. We'll shoot 30. Wait, did I say 2010?
I don't know.
No,
Lots,
30 years, over 30
okay.
years.
Lots of things going into this. There's politics, there's economics, there's all sorts of things, but the realization somewhere here, if we want to say, like, this is about 1930, let's say 1920, 1930, of like, our cities are incredibly dirty. That the air quality's bad, that just living in town is endangering the kids. But hey, what else have you got? There is nothing else. And then, you know, following on, there becomes the political will and the economic will to find alternate sources. So we start seeing wind power, wave power, solar power. It takes a while to come along because we don't have the technology for it, we don't have the materials for it. But there's a willingness, and then natural gas is probably where we lean first. And then certainly in the UK, but not in other places necessarily, the miners' union becomes when your energy, the energy of your entire country is due to one set of workers. And you can't have steel without it, you can't have shipbuilding without it, you can't have electrical generation without it, you can't have home heat without it. They become incredibly powerful. And over the 1960s and 70s, they asked for pay rises, I am not kidding, 30% a year. They want a 30% increase. And when the government says no, they go on strike. And it just completely pummels the country. They give them 30%, and you know what they ask for next year? 30% again, or 25%, and it's year after year after year. And then we just have a person come in and say, no more. We now have the political will to switch to an alternate fuel, and we see natural gas come in and just completely decimate that industry. Yeah, so politically, there's a hand in this as well. Not in the US, but certainly in my home country. Okay, so the man-made part is the smoke. The coal was the dominant fuel of the entire era. You could dig it out of the ground. It's not like oil, where it's immediately dirty and then has to be refined. You dig it out of the coal and out of the ground and you use it, and you can pick it up with your bare hands, and you can have it dropped off at your door. There were coal deliveries to people's houses, so useful, right? And cheap and plentiful. And the smoke contains particulate matter. Okay. And we will talk as the book progresses through this chapter. It talks about sizes of particulate matter, and big particles, no problem. Tiny particles, not a problem, but particles somewhere in the middle, problem, because they're big enough to breathe in, but we don't breathe them back out again. The particulate matter from the smoke. So this is the main cause. I was saying, London, I may have said it in this class, I've said it somewhere else recently. The images that you see on television of the big buildings in London, like Westminster Abbey and the Houses of Parliament. When I was a child, I thought those buildings were black.
Yeah, I think you did say here.
Because they were black when I was a kid. I didn't know that they weren't black. They're actually a beautiful sandy color. They just had decades and decades of smoke on them. And this is from, power stations, no problem. Industry, no problem. But houses, every house in every street had a coal fire. And every coal fire was started with wood and paper. And you get all of that particulate matter going up into the air where the natural part comes along, where it's cold. And when it's cold, the air stays where it is. There's no convection currents to take the warm air back up into the sky and circulate. The cold air, and especially if it's a bit damp, which is damp and cold there all the time for months at an end, that air is stagnant, and now it's full of particulate matter, it's full of smoke, and we get industrial smog. Okay. Several people will lean into, oh, it was the industries doing it. It's as likely that it was household than anything else. Clean Air Acts all across the Western world mean this is gone. So I can look that up, and we'll in the US, when is the US Clean Air Act? I think that might be a Richard Nixon thing.
Yeah, I think you're right.
The next chapter out, chapter 4, has how we legislated against it. But we had a series of parliamentary or legislative acts that say you can't do this. You have to find an alternate way. Things that don't even get used anymore. Mitigation for this. There are things called scrubbers that would be on the top of a chimney stack. And as the smoke is coming out, we have a way of pulling stuff out. We went through that. Okay. That's the first one. This happens in cold climates with unregulated access to fossil fuels. Where it's still happening, India. There's a number of times when I've been in India and I have to take a long car journey from somewhere to New Delhi. And you'll be in the car for hours and hours, and you know when you're approaching Delhi because your eyes start to sting. Because the smog is so bad, and usually the time that I visit is in December when it's cold. This is another occasion of the industrial smog that the low-income families that are subsisting collect wood. They just collect scrub wood, and then it's cold at night, they burn the wood. And so now there is wood smoke in the cold air at nighttime, and when daylight comes, you can't see you can't see a thing. Goes with, in early morning, fog conditions also in India. And so the international flights out of New Delhi, they don't fly during the day because they can't get out because they're fogged in. If you want to fly out of New Delhi, your flight leaves at 4 a.m., 5 a.m., while it's still dark, before the smog has taken over. Yeah, there's been numbers of times where the plane has turned around because it can't land. Yeah. That type of smog is so unimportant to the US that it gets a footnote in our textbook, but it is very, very important to other parts in the world. The one that the US worries about is photochemical smog. And photochemical smog, again, is partly man-made and partly climate. The man-made part here is largely the internal combustion engine. It's mostly that. And then the climate part is largely cold in the morning, sunny in the afternoon. You need clear skies. Again, it's a combination of man-made effect and a natural climatic effect. What's going on here is everybody drives their car at the same time. It's not enough that there are just lots of cars. They all have to be on the road at the same time. And they have to be on the road at the same time when it's cold. And it's cold in the morning. Okay. It's cold in the morning and the cars are on the road in the morning, then the emissions from the tailpipes in the cars meet the cold air. The cold air is more dense than warm air. So if this is my city and here are my cars, whatever it is that I'm building up, whatever the emissions are, they stay here. They don't get the chance to ride a thermal and mix in with, do all the diffusion stuff with the atmosphere. Same as with the other type of fog. industrial fog happens when it's cold. The cold keeps the particulate matter close to the ground. Here, not necessarily particulate matter. The stuff that I'm worried about, there's a couple of different things. Yes, there's some particulate matter, mostly from diesel engines. But here's something you know. Volatile organic compounds. We burn octane. Gasoline is largely octane. That's an organic hydrocarbon. And our cars aren't perfect. Every time you squirt some hydrocarbon into the piston and burn it, you don't get complete combustion. You don't make, so complete combustion would be, I make only carbon dioxide and water. I take a hydrocarbon. Actually, I'm going to write the chemical formula for hydrocarbons fall into this generic. For every number of carbons I have double the number of hydrogens and then an additional 2. Okay. Different families of hydrocarbons exist. This is one of the big ones. These are called saturated hydrocarbons or alkanes. A complete combustion makes only carbon dioxide and water, which in terms of smog pollution, we are not worried about. In terms of other things, we will be worried about this one later, but not right now. Some of this doesn't make it through. Also, the fuel that you buy isn't clean. It isn't scrupulously clean. It contains some sulfur. And that sulfur makes its way through the combustion. You're going to burn it and pressurize it and make it hot and then blow it out of the tailpipe. And it is going to come out as sulfur oxides. This X right here represents a number. The number that we're worried about, really worried about, is 3. So this is going to be either SO2, sulfur dioxide, or SO3, sulfur trioxide. SO2 is bad, SO3 is nasty. Also, you just can't help it. 78% of the Earth's atmosphere is nitrogen. When your car takes a gulp of air and a squirt of fuel to burn in the pistons to make carbon dioxide, to push the piston out, it also takes a gulp of nitrogen. Now, we've spent a little bit of time talking about this. There's a triple bond in here. That nitrogen is largely inert. But if you put a spark through it and then have other high energy events happening, flames and stuff happening around it, some of that is going to combine with the oxygen and make nitrogen oxides as well. The number of possibilities for nitrogen oxides is huge. We can have N2O, NO, NO2, NO3, and then there's a bunch of other ones as well that have 2 nitrogens and 2 oxygens. Whole bunches of nitrogen oxides. Okay, so this X can be, NOx just represents them all. All right, I got all of these things. I've got the unburned hydrocarbons, I've got sulfur and nitrogen, plus particulate matter. Okay. And this grows to be a particular concentration of material in the morning when it's cold. And then in the late morning, the sun comes out. And the sun does UV things to this. And the big culprit gets to be ozone. That the ultraviolet is going to split some oxygen somewhere, and we're going to make ozone, and we're going to make a couple of other things, and they are going to chew through this and give us smog. And we see this in Los Angeles. Los Angeles, I've never been, but I see TV images of it now versus TV images of it 40 years ago, when you see the buildings and the horizon, and look at our beautiful town, and it's all yellow, just a yellow haze of the yellow's probably from this.
It's also banks up against mountains, and you have the valley that's right on
Mhm.
the outside of it, so everything from
Yeah.
the ocean just gets trapped right
Yeah.
over it.
So you're right on the ocean,
Yeah.
right? Why doesn't it blow away?
But,
Well, because it's trapped.
yeah.
Yeah.
It gets
So-
really nice and incubated, essentially. Yep.
Yeah, that's part of the reason. So like I've toured the Northern California, and they say, oh, wine grows here because the fog gets trapped in this valley and it does this thing. Yeah.
That's why I lived in wine country.
Yeah.
So.
Mm-hmm. Okay. All right. But anywhere where you have a combination of cold mornings, lots of cars, and sun in the afternoon, you're going to have ozone action days. We don't get very many of those in Austin. Why not?
We're relatively flat,
Yeah.
right? I mean, that's partly, we're also in the Midwest, so we have a lot more wind. I know, or like we're in the middle area.
I think it might be that it's never cold enough in the
Oh,
morning.
it's just the Earth's just never cold enough also.
I think that it might never ever be cold enough in the morning.
It's colder in Temecula in Southern California on average, I'm pretty sure,
Okay.
in the winter than.
We absolutely used to have them in San Antonio. That everybody's in the car in the morning, and it's cold in the morning, and then it's going to be sunny in the afternoon. So there are days when they're called ozone action days. What do you do on an ozone action day? What are they expecting you to do? What's the action part of the ozone action?
To not try, or to carpool, right?
Yeah. Nowadays, post-pandemic, this would be a work from home day. That wasn't even on anybody's consciousness prior to the pandemic. But yeah, it would be, can you go in later? Could you carpool? Could you take one car instead of multiple cars? Because if I take anything out of the chain, I mitigate what's happening. And the thing that I can't stop is the sun shining down on here. But again, you don't get ozone action days. There you go, just stopped it. Put a cloud there and stop it. So you have to have both things going on. The EPA allows a certain number of ozone days per year until they act. And when they act, it's never good. They do things like take away highway funding. So local government, which relies on always expanding. It's apparently the job of local government to always be expanding everybody's economy, which means build more roads, build more infrastructure, do more visible stuff, okay? Which for us means more individual cars. If we take those away, then local government feels the pinch from it. Okay? So there is pressure on local government, and all politics is local, said somebody very smart one time. That, yeah, if I want to achieve anything globally, I pressurize at a local level and get stuff done. We can look that up. It's certainly in the next chapter out. Chapter 4 is, so 3 is the science of what's going on, and then 4 is what are we going to do about that? How does it affect people's health? And then 4 brings in acid rain, which isn't in this chapter. Okay, let's look at a little bit of the science. Oh, there is a part. This will definitely be part of a homework, a quiz, or a test. On page 71, it says there's no good way of measuring stuff that's in the atmosphere. And when somebody is talking on one hand about particulate matter and then on the next hand about gases, one's a solid, one's a gas, how are you going to measure those and then talk about them in the same sentence? So there's a couple of different options open to us. We can go full science on this and go molarity. We can count identities of materials and then turn those masses into moles and then moles per volume. That's usually moles per liter, but we could do moles per cubic meter or some other way. Okay, we could do a concentration. But to do moles, you have to actually know what the identity of your material is. You really have to know. So what if it's just all unburned hydrocarbons? I don't know what they are. Then there's a couple of options open to us. We could just use grams in a volume. That will work, because that way we don't have to know an identity. And we can do parts per million, and then parts per billion, and even parts per trillion of if I took 1 billion particles of gas, how many of them would be of this particular type, this particular identity. And because there's an Avogadro in there somewhere, page 71 has a 2-page box about if you gave me micrograms per liter, could I turn that into parts per million? And the answer is yeah, absolutely you can. So we'll pull that out at some point and do that. It also says stuff that we know and we've hinted at multiple times, right? Mm-hmm. That our atmosphere is 78% nitrogen, and that really is inert. It's not doing very much. The only way to get nitrogen to do anything at all is to hit it with a lightning strike, because that's a triple bond. Okay, there's 3 covalent bonds between those 2 atoms, and it's non-polar, So there's nothing at one end that you can grab onto that feels different from the other end. So you really have to hit it with a direct form of energy, like lightning, or the spark from an internal combustion engine.
Right.
Okay? And we have 21% oxygen, which we think automatically, so this is O2, right? We automatically think of oxygen as being oxidizing. But oxygen's a stable molecule as well. You can't get to be 21% of the Earth's atmosphere and be reactive. So it turns out that even though we have 21% oxygen in the atmosphere, this is not the thing that's doing most of the high energy reactions. It's going to be something else. It turns out to be a radical. It's oxygen hydroxide radical. Oh, and one of the other things, our book's mentioned it a couple of times. I've said it out loud once or twice, but I've used it in a different way. We've meant the same thing, but I've said it a different way to the book. I have said things like, there is no biological metabolism for nitrogen, not in higher life. There are nitrogen fixing bacteria that take nitrogen out of the sky and turn it into ammonia. But we breathe in nitrogen and we breathe it all back out again. We have no metabolism for it. How our book says that is they call that a sink. There is an absence of a sink, that there is no mechanism by which that molecule gets to come out of the sky. Okay.
So sink spelled
S-I-N-K, as in,
It's going.
yeah. The way that this comes up the most in almost general public speak is heat sinks. That your computer generates a lot of energy, and then you pull that energy away into a particular component called a heat sink. Okay. And the process of being pulled out of the sky, so here we go. Here is a gas. And the gas is going to go into a sink. And then what happens in a sink is it gets biologically, usually, I mean, it could happen chemically as well, recycled. Our book says destroyed. I prefer recycled, because the atoms don't get destroyed, they just get repurposed. They get shuffled around a bit. This process has a word, has a name. It's called fixation. Fixation hasn't popped up yet in our book. I'm assuming it'll pop up later. All right. There is oxygen in the sky. That oxygen has to be involved somehow in oxidation, because that's what the very name of the word means. In the simplest sense, oxidation is a gain of bonds to oxygen. That, in its simplest sense. In the chemical sense, it's much more complicated than that. It's nuanced. That oxidation is the loss of electrons. Okay, we're not going to be counting electrons. We're not going to be following them. We're going to see that, hey, my product has more bonds to oxygen in it than it did when it started as a reactant. Therefore, it has been oxidized. Okay. So, we we have quite a lot of oxygen in the sky, but there's a double bond between those two oxygens, which means its EA is very, very high. What's EA?
Activation energy.
That's the activation energy, and the activation energy is the absolute barrier required to get over before a reaction will initiate and do whatever it is that you want to. Even if I have very high energy reactants and the possibility of making very low product that are low in energy, so energy versus time, if I have a massive activation energy, EA, I really have to try very hard in order to make the reaction work. Well, I'll get all that energy back, plus this amount of heat change that we call delta H, enthalpy change. But in order to make it work, I have to put a lot of energy in. And because oxygen has that very, very stable double bond, its activation energy is just too high. So it's not the culprit. It's something else. It's this hydroxyl radical. Okay, let's just revisit what it is to be a radical. What's a radical?
It's how an electron dislodged, right?
Yeah, so it has an unpaired electron.
Unpaired electron.
Now, oxygen has multiple electrons that we haven't yet drawn, and they don't count. They're not going to be the ones doing any of the work here. There is an unpaired electron here. Okay, so oxygen, group 6. 1, 2, 3, 4, 5, 6. If I go ahead and make water out of this, there's 2 hydrogen atoms, each from group 1 with 1 electron. I make a covalent bond and I make a covalent bond. Okay? But if I remove one of those hydrogens and it takes its electron with it, this pair of electrons is being used in a bond. This pair of electrons is a lone pair of electrons, a non-bonding pair of electrons, as is this one. So they're all reluctant to do chemistry, but that one right there, oh boy, is that one reactive. Because all it has to do is find one electron by making one covalent bond, and it'll have 8 valence electrons. And so this guy is going to just react violently until it finds an electron. And if by finding that electron, it rips an electron off something else, then all it does is pass the radical torch onto something else instead. That's where we get into so much trouble. Radical reactions work the best when they're in very low concentrations, because then the radical just churns through stuff and just passes its radicalness on. Radicalness is the first time anybody in recorded history has ever said that word. Well, this hydroxyl radical has a much lower activation energy because it's unstable, reactive, low activation energy, guaranteed to react. Okay, let's see how we get there. And again, it's ozone. Here's ozone. If I give it UVB, actually I think I might have a path somewhere else. No, never mind. We've seen a number of variations of these. If a reaction involves light energy being the cause of something breaking, so I have 3 oxygens atoms stuck together in a molecule, and I break one of them off. So that's the lyse part right here. That means to break. So this is a photolytic cleavage. This is a photolytic dissociation or photolysis. Okay, that generates this guy. Well, not only is it going to be have unpaired electrons, it's also in its excited state. There's a fabulous piece of oxygen chemistry that we might have the option to see. That's the difference between a triplet state and a singlet state. About when you take the electron, we were talking about it in another class today. When you take electrons and you promote them, that you don't keep the spins in the direction where they go, you do that. And, ooh, that's a difference in energy that you can feel. This is photolytic. That means this reaction happens in the daytime. And I'm going to take that excited oxygen atom and react it with water vapor and generate 2 of these hydroxyl radicals. Okay, our book doesn't describe what I'm about to say in these terms, but I think that other people might, and when I see what the book is trying to say, this would be how I would describe it. I'm going to talk about how fast that reaction works by ascribing it something called T-half. What is T-half? This is its half-life. What exactly does that mean?
It's the time it takes for it to decompose, or
I'm not going to use the word concentration, I'm going to use the word amount. Because we just said 10 minutes ago we could use concentration, but this particular branch of science is muddled with so many forms of measurement. I'm just going to put them out. the amount for the original initial amount of reactant to decrease to half or by half. So if I had 100 grams of it, it would be the time that it gets to be 50 grams. And then by rule, if you started counting at 50 grams, it would be the time that it takes to get to 25 grams. And that time interval would be the same amount of interval. Okay. The half-life for this second reaction is less than a second. Yeah. So the first step is rate determining. We're not going to hit the kinetics of this, but that first step is rate determining. And you can let that one stew for however you like, but those excited oxygens are making this. Okay? That's going to happen really quickly afterwards. Okay, let's introduce this guy. This is our culprit. Let's introduce that to all sorts of things. It's carbon monoxide. I'm just pulling a couple from the book. And here's my hydroxyl radical. And it makes, well, that looks a little bit strange. Carbon. Carbon always makes 4 bonds. Well, oxygen only makes 2. There's a triple bond between those carbons and those oxygens. It's a little bit tricky, this. This is a kind of cool one to look at. Carbon monoxide is a very, very interesting molecule. We're going to take the 2 unpaired electrons that an oxygen always has, which usually leaves 2 non-bonding pairs of electrons, 2 lone pairs. We're going to make a double bond, and then we're going to use one of the lone pairs to make another pi bond on top. So we get lone pairs on both ends. And inorganic chemistry, one of those lone pairs of electrons is much more useful at making bonds than the other. Yeah, the bond comes out of that end, not that end, which isn't immediately what you might expect. This is a radical. This is what makes it a radical, the unpaired electron. And then hydrogen always makes 1 bond, oxygen always makes 2 bonds. Carbon is supposed to make 4. Which means there has to be something there. That carbon right here, it's still a radical. Still has an unpaired electron. Which is the deal with radical reactions is they're very fast, they chew themselves up, but they pass their radical behavior on. Okay. Well, that is not going to last for very long. This guy, so if this is step 1, we got to follow on that plus oxygen makes, let me write this down properly. There's a carbon dioxide to be made here. We're going to make that, and then we're going to make this one. Okay. Now, if anything, we've made this worse.
Mm-hmm.
What do we know? So, there's a couple of things that we know. Along the way in chemistry, we know this is dioxygen. And it has a sigma bond and a pi bond, and that is stable. And one of the things that we learned very early on is that, hey, there's not a lot more stable than that. Double bond, very good. Oxygen loves to put a double bond between itself and another oxygen. And then we see this. What's this called? Yeah, that's peroxide.
I always confuse that for some reason.
And peroxide hates having a single bond between those two oxygens. Molecules don't hate or love. This gets a happy face. This gets a frowny face. There's very little that oxygen likes less than making a single bond to itself. And yet, here we are. This is a peroxy radical. Technically, this is a hydroperoxy radical, because that H could be replaced by anything, but hey, it's a peroxy radical. Okay. That peroxy radical is going to react with anything it meets, whether they want to or not. I've got space for a line 3 at the bottom.
Mm-hmm.
Let's do a line 3. Okay, so first of all, what we've done is we've passed on the radical to something else, which has then passed it on to something else. And then here's where the destruction shows up. Here's the peroxy radical. And then, how about one of those nitrogen oxides that came out of the tailpipe of your car?
Mm-hmm.
How about we oxidize it? It was this much oxidized, and we oxidized it more. What did we say that oxidation was?
Gain of a bond, right?
Increase in the number of bonds to oxygen. This nitrogen is bonded to oxygen 1 time.
Mm-hmm.
This same nitrogen is now bonded to oxygen 2 times. That's an oxidation. And we've lost an oxygen. And back to making the peroxy radical, the hydroxy radical. So this Good thing, bad thing?
It's, I guess it would not be the absolute worst, but it depends. I mean, it's not good. The radicals aren't good, but
Yeah, yeah. We as biological entities want to stay away from as many radicals as we can possibly avoid, because they just chain react. It goes in, it does, let's call it damage, does damage, oxidative damage, and then it comes back out again. It's a chain reaction. It's not consumed. But it's a way of taking whole bunches of reactive or semi-reactive molecules out of the atmosphere.
yeah.
So what about like, hey, all of those carbons that never really burned and now they're floating around. Yeah, actually you can walk past some cars and they're out of tune. You can smell the gasoline coming out of the tailpipe. Like, dude, you are not burning that fuel. I can smell the fuel. Where does that go? What happens every time I fill up my lawnmower and I spill the gasoline all in my driveway, and 50 seconds later it's all evaporated? Where did it go? Okay. It's in the atmosphere and there's no sink for hydrocarbons. But if I could burn them without actually flame them and combust them and turn them into carbon dioxide, then I can get them back. So this is responsible for removing all sorts of stuff from the atmosphere. Turns out nothing is ever, apparently nothing is ever done. All right, so we had something on the board about it, something being really, really quick.
Oh, the half-life of.
Oh, which step was that? Let me have a quick look. Oh, that was the hydroxy one. Okay, there's another quick one. All right, at the bottom of page 75, within a few minutes, most of the nitrogen dioxide, NO2, that was produced in the hydroxyl radical peroxy radical cycle that happens during the daytime, within a few minutes, that NO2 absorbs ultraviolet light and dissociates back to NO and generates an oxygen radical. From the viewpoint of the nitrogen oxides, the cycle of NO oxidation and reduction of NO by sunlight, it's a cycle. So this guy, let's do 4. NO2 do I need, no, I don't need, I just need ultraviolet.
Yeah, UVA.
Makes NO, NO. It's a big, big cycle. This can only happen during the daytime. Because here's the photolysis. Anything that has the photolytic part can only happen in the daytime. And in our book, what is that, 75, 76, there's a little cycle that says NO in, NO2 out, NO2 in, NO out, and hydroxyls and peroxies. You could also link that to ozone if you try just a little bit. I took that diagram and I kind of extrapolated from it a bit. And I think we can get this. All right, I'll start. I'm going to put stuff here. I'm going to start the way that the book has it. If I have NO, I can get to NO2. In order to get to NO2, I have to feed in the peroxy radical. Biology do those cycles where stuff goes in, stuff comes out, yeah? Okay. Hydroxyl radical comes out. O2 goes in. And then UVA pushes it back the other way. But UVA, when it pushes it back out, gives us oxygen. Oxygen atoms. Which then with oxygen in gives us ozone. I took 3 separate things and stuck them together. And I don't know if that makes it better or meaningful or worse. I don't know. Oh. Okay. 79 shows hydrocarbons and oxygen turning into carbon dioxide. It goes on to say all nitrogen oxides can be collectively called NOx. And then it talks about Mexico City being a place for photochemical smog, as are obviously other places. Chinese megacities. Doesn't mention Los Angeles yet.
Oh,
It's got to be in there.
3.5.
Yeah.
Yeah.
Canada, the Great Lakes, the Midwest, New York, Houston, Los Angeles, page 86. And then where we'll pick it up, page 87.
Okay.
What to do? What to do? How about we limit the amount of unburnt fuel? How about we limit the amount of nitrogen oxides by building better engines, catalytic converters, lean burn engines? How about we legislate? You know how Europe deals with this. It's a very un-American way of doing it. You make gasoline cost $12 a gallon.
Yeah.
And
We
it's
sort of do it with taxes.
no, you don't.
Not really, though.
At $12 a gallon, everybody drives small economical vehicles that do 60 miles to the gallon. I'm not kidding. The Ford Fiesta that they sell in England does 60 miles to the gallon. The same car that they sell in the US does 22. It's called social engineering. You tax people until they behave in a way that is beneficial to the entire country or entire region. But that is a decidedly un-American way of doing things, because this is a land of individual freedom. Okay, we will pick that up because there's a political aspect of this involved, and we'll pick it up on page 86 next time.